So I'm not completely sure what this has to do with this class, except a wind tunnel, of course, and in a slightly different configuration. If you've been to Vegas, you've seen these things. It's just a big duct that forces a bunch of air up, enough air to be able to, against the drag of the air on your body, or people's bodies, to be able to support them against the weight of gravity. I mean, that's the basic force balance that's in place here. And so in this case, the critical parameter which would be controlling this would be the Euler number. The Euler number, you might recall, is the ratio of pressure force to inertial force. And so it's just the P over gamma term and the guy doing push-ups on bottles. That looks like a smart move for the morning. And so it's really just the velocity squared term and the pressure term. So the same as a gust of air out of the jet engine hitting the truck that goes behind it. It's the same calculation. The Euler number is basically the number that comes out of the juggling of the pressure upstream, pressure downstream where it stagnates on the truck. You kill velocity, and the force on the truck is applied. The pressure on the truck is applied due to that destruction of momentum by killing velocity. And so a lot of the things that we're kind of suggesting here, when we look at dimensional analysis, which is what we're dealing with, is the opportunity to be able to do experiments typically at a different scale. So you use a replica of a car, a scale model. You perhaps flow air or water over it, and from the measurements maybe of the forces that are applied to that model, you can upscale those in some rational way to be able to say what the forces would be in real life. And then if you know what the forces are in real life, then you know you need to apply that force at that particular velocity to be able to physically move it through the air. And if you know that force at that particular velocity, you can figure out exactly what portion of the power, the product of force times velocity, would be that you'd have to power that car just to get over air drag. And so you could see, what proportion of your energy consumption, if you like, fuel consumption, would go as a result of that. So that's a typical example of what we might be interested in. And I don't know whether this worked last night. It was experiencing interruptions. But you can imagine doing these experiments on a whole bunch of different things, and including things like soccer balls. And so I think that's exactly what they're doing here. Perhaps we won't spend too much time doing it, but you'd be interested to know what the drag is. So if you wanted to have a soccer ball that went really quickly, I suppose you'd want to maybe change the arrangements of the pleats on it, or the seams, I guess, to be able to either make it go faster, presumably, if you have fewer seams. Although the interesting thing is, as we'll find out, the reasons that golf balls are actually dimpled is that you want them not to be smooth. A smooth golf ball would probably not go as far as a dimpled golf ball. And the reasons for the dimples are that it sets up a kind of boundary layer, which actually makes this turbulent fine layer around the ball, which allows it to go actually with much less drag, and therefore it can be driven further. And so the reason for dimples on a golf ball, perhaps there's dimples on this soccer ball as well, are related to that. And so it's kind of some interesting non-intuitive, counterintuitive components of behaviors. But the bottom line is we'd like to be able to scale things in some way. And so in what we're talking about here, that's really what our attempt will be to do. And so let's just summarize exactly what we talked about last night. I alluded in this start off here that if you're talking about, for instance, these guys in the Red Bull component behavior, if you remember Darcy's law, if you remember Bernoulli's equation, and if you write this upstream and downstream, then you know that if you're looking at the forces that are applied on something, like someone standing here, and a velocity that is applied at them, then the pressure that's applied on that person you'd get by just defining the upstream pressure atmospheric, the downstream pressure we don't know, the upstream velocity as something, the downstream velocity as 0, and you'll end up with the ratio of those, which are really the components in the Euler number. And so we said last time that the two properties that we probably will find most useful when we talk about dimensional analysis, in fact they'll almost always come out this way, are one is the Reynolds number and the second one is the Euler number. Reynolds number is important because it indexes the flow. And so if you take a snapshot of exactly what the flow would look like at a given Reynolds number, which is this figure here, then it will have a certain configuration. If you increase the Reynolds number from 2000 to something else, it will look slightly different. So if you want to get the exact flow configuration that would give you the appropriate forces that are applied on the structure, you have to do the experiment at the right Reynolds number. So that's the issue number one. At very low Reynolds number, the flow regime, as we talked about last time, would be a creeping flow regime where it would just hug the cylinder and go off the other side without all of this turbulent wake in the background. So this would be at a Reynolds number, say for sure it would be at Reynolds 1. The question is, where does it start to deviate from that? And we'll talk about that in due course. The second is that if you're doing your experiment at the right Reynolds number, so you have exactly the right flow configuration, then you'd like to know something about it. And so typically what you want to know are the forces that are applied to the structure. And typically the forces are given by taking, if you're a medieval knight, then the forces on this shield are just going to be the pressure times the area, which is equal to the force. And so this pressure term here, if you know what area it's applied over, gives you a force as a function of the velocity squared. And you see some interesting scaling things here, and that is that you could surmise from this that the force is proportional to the velocity squared. And so that means that if you double the velocity, you quadruple the force that's applied to it. And so it's not a linear relationship. You can't necessarily define that from this, but we'll find out that that really is the case. So if you're free falling through air, if you're going at 1 meter a second versus going at 2 meters a second, the forces applied onto you as drag will be quadruple, not double, as a function of that. And so those are the two principal ones. The Froude number or Froude number is used to be able to define behaviors where we have free surface flows. And so we've always looked at the idea of for a different reason, our fireboat being dragged through water. So where you have a free surface, and typically where you develop a wave, a bow wave, and a wake behind you. A bow wave elevates it, so you can imagine that as you push a boat through water and you create a hump in front of you, which you really have to climb over, the boat becomes less and less efficient. And so this is where gravity is the main force that's driving this flow, right? You pile this up, you're bulldozing this water up in front of you, and you're acting against gravity that's trying to push it down. There is no fluid pressure locked in there, it's just gravitational, the weight of this small bump that you're having to activate to be able to drive this boat through. So Froude numbers are of use when you have free surface flows, if you're towing a boat in a water tank. Okay. All right. So what we'll do today is we pulled these out of a hat kind of last time. You remember that we derived these based on Bernoulli's equation. Pressure term, velocity term, elevation term or gravity term, and also a viscous loss term. And from those four terms we got all of these expressions. We did that last time. And so that's where they come from. How do we define the question now is, how do we define the appropriate dimensionless groups that will describe a particular behavior for a system we're interested in? Yes?
Isn't the head not supposed to be downstream?
Yes. But, okay. Yeah, it isn't downstream, but so. Yeah. So the question is there a formalism that allows us to do this? And so there is a formalism. It's called Buckingham pi, named after I don't know, an 1800 scientist, Buckingham, again British, I think. And so the system that we might look at is one which we could look at, which we kind of alluded to last time, which is flow in a pipe. The pipe has some diameter. There's an average velocity flow in this pipe. Same velocity out the other end. The material properties that relate to the flow, you could add some others. I guess you could also talk about compressibility, but it probably won't be important in this case. The length over which the pressure drop occurs. Which is driving the flow. And those are pretty much the behaviors that we would define this. We know from talking about the Navier-Stokes equations and the energy equation, which is the most complicated form that it comes out at is Navier-Stokes, which is that the average velocity is related to the diameter squared, 32 times the viscosity of the fluid that's flowing, and the pressure gradient that's across the length of this. And so that's an expression that we have. So we don't actually need to do this Buckingham pi relationship in this case, because we could manipulate this. The other thing that's perhaps interesting to think about is that in the same way that we can think about this tube with an internal flow, when we're talking about pipe flow, you could imagine this as being a sealed tube, which is being impacted by a velocity, maybe an average velocity, and where the flow goes around it and comes out back the other side. A bit like our cylinder, but now instead of being a cylinder, it's a long cylinder, and it's a different aspect of it. And actually, the same kinds of behaviors you'd expect. There'd be a pressure change between here and the backside. In this particular case, the pressure difference is really driving the flow along here, and it's really driving it against shear stresses that are applied on the inside of this pipe. This is our viscous effect in the Reynolds number. And in this particular case, the shear stresses are applied against, I guess, let me draw it on the outside of this pipe, but it's the same thing. One's inside and one's outside. So in all cases, we're really doing work against viscosity. In one case, the viscous flow is on the inside of the pipe, and the forces are therefore applied on that fluid inside the pipe. If it's an aircraft wing, which this would be a surrogate for, then the drag forces are on the skin of the structure. So internal flows, pipe flows, we'll spend 2 weeks dealing with those. External flows, we'll spend 1 week dealing with those, but really it's the same problem. And it's the same problem in that, in the same way that we talked about these important non-dimensional parameters, the Reynolds number is the one that figures exactly what the flow regime will look like, and the Euler number is the one that will be able to, bless you, will be able to define the magnitude of the forces that are applied on it, which we typically want to know. Whether the forces are drag, if they're aligned along this tube, or if they're lift, if they're perpendicular to it, as in a wing, then that's what we'd like to know. And so what we would like to deal with this is that if we've said that these are the important parameters, the question is, can we rearrange this expression in terms of those important parameters? And so if we take it on trust that we can look at something like 1 over the Euler number plus the Reynolds number. And so this comes back from, I think there's a figure here, this figure here. So we'll come back to this. And basically the idea is that what we could do is we could do a whole bunch of experiments. So dimensional analysis is all about figuring this stuff experimentally. And so what we could do is we could take a pipe of a given diameter, take a fluid of a given viscosity and density, and we could flow it at some pressure, and we could measure the velocity we get at that pressure. We could change the pressure that drives the flow, we get a different velocity. We could change the pressure that we drive the flow at, we get a different velocity. So that would be fine for that particular pipe, that particular fluid that we're using, and that would give us one curve, one unique curve. If we change the diameter of the pipe, say we made it a larger diameter pipe, then what would we expect? Larger diameter pipe, you'd expect intuitively that with a same pressure gradient, you get a larger flow, maybe a larger flow velocity, because now it's further away from this zero velocity boundary condition at the edges. So if you have a larger pipe for the same pressure that you'd apply, you'd expect maybe to get a larger velocity. For the large diameter pipe, again, at a larger pressure, maybe a larger velocity. Likewise for this. And so you'd get maybe a second curve. For this is D1, this is D2, and in this particular case, D2 would be greater than D1. And you could repeat it. And so you could do it for every size pipe you could ever imagine. You could also do it for changing the density of the fluid. Might not make much difference. But if you change the viscosity, if you took pipe D1 and now you change the viscosity so the viscosity is larger. Again, for a given pressure gradient, if you increase the viscosity, maybe you'd expect if you're running treacle or honey instead of water, you'd get a lower velocity. So if you change the viscosity and you increase the viscosity, then for a given flow rate, perhaps for D1, you'd expect to get another curve. So this would be D1 at mu 2, and this is D1 at mu 1. And again, mu 2 would be greater than mu 1. And so you'd end up with a whole sea of these curves. You'd actually completely fill this figure for the infinite set of these curves that would do that. But what we'd like to do is instead of have a figure for all of these individual variables, we'd like to have a single figure, maybe with a single curve on it, which would suffice. And so that's our interest in being able to figure out what the non-dimensional variables are that would allow us to do that. And so we're going to attempt to do that. We're making the assumption that Reynolds numbers and Euler numbers are the two important things, only because I've said that they are, but it includes pressure and velocity squared. So let's see if we can rearrange this expression to get that. I wish I had a different color pen, but I don't. So let's write this out with a bit of space in here. Is that a reminder coming into me or something? Over dp dx. And so what am I going to do? Well, viscosity is here. So this term on the right-hand side, probably we'd like to get to look like Reynolds number. It has viscosity on the bottom, so it's already set up like that. That means that this term on the right-hand side will be the reciprocal of Euler number, maybe. And so if we want to get that, how do we get that? Well, Reynolds number has viscosity, it has velocity, it has a length, and it has density. So for sure, we have to multiply by a velocity on both sides. We have a length here. Let's take, well, we actually have a length here already, so let's not worry about that. We don't have density, so let's multiply both sides by density. And is there something else I need? Yeah, okay. And so the Euler number on the converse side needs to have pressure on it. It needs to have pressure on the bottom. So let's divide both sides by dp. Okay. And so now, certainly this is pressure divided by rho v squared. So reciprocal Euler number. And so let's see what we can make out of this. We've got a pressure here we don't need. We've got, yeah, and so let me write this out as rho v squared over p dp. Let's not worry about that. This isn't a negative. And that's equal to, let me write this as 1 over 32 for this. Let me take this d and this dx and write it as d over L, where this is the length. And what are we left with? We're left with another d, we're left with a v, and we're left with a rho, and hopefully we have a viscosity. So we basically have 1 over the Euler number is equal to 1 over 32, the diameter to length ratio, and then this is Reynolds number. And so now we have a unique relationship between these. It happens to be for laminar flow within a pipe, so one where we don't get turbulent behavior going. And so if we plotted that, I guess as Reynolds number increases, Euler number will decrease, so I guess we get a curve like this, right? It has to be some curve. So this would be this relationship, this boxed relationship. And so all we've done is we've been guided in our choice of variables that we'd use for experiments by dividing them into appropriate groups. And so now, instead of doing 5,000 different experiments on 2,000 different pipe sizes and with 20 different fluids of different viscosities, we could, in theory, hone in on just doing one set of experiments, one diameter pipe, one fluid, and we could fill out this curve, and this curve would be fantastic for every single fluid we could ever imagine. So that's the power of dimensional analysis. We happen to start with an equation that defines it for the simple case. And so you might say, why do we care about dimensional analysis if we know exactly what the behavior is? Well, this expression is only true for what we'll refer to as laminar flow, where the laminae of the fluid slide very nicely over each other. There are no turbulent eddies in it. But the fundamental parameters of Reynolds number and Euler number are still appropriate parameters, even when we have much higher velocities and turbulent flows, in which case we can only get the true results by doing these experiments rather than relying on the simple conditions of this simple equation. So it's an incredibly powerful technique to be able to do it. So there is a formalism to do this. Typically it will end out that the main parameters that come out of it will be a Reynolds number that indexes what the flow regime looks like, and an Euler number which defines the pressures on the structure. And you can do it just by inspection, but there is a formal way of doing this. And the formal way of doing this is called Buckingham pi. And it relies on the fact that you get these pi groups, which are just called pi numbers. And so we'll do the same problem and assume now that we have no knowledge about any equation which defines this behavior, but we'll use this formalism to be able to do it. So quoting here from your textbook, if an equation involving k variables is dimensionally homogeneous, it can be reduced to a relationship among k minus r dimensionless products, where r is the minimum number of reference dimensions used to describe the variables. So what does that mean? We're solving our problem for a pipe. We've defined the variables of this pipe are that we have a change in pressure. So in this particular example, taken from the book, the change in pressure with length is actually dP over dl, dx, I guess, along the pipe. The pressure gradient, so that's this term here. I didn't notice this, but maybe this is for the duct, doesn't really matter. This is the diameter. This is the average velocity, v, and density and viscosity are the same as we had. So if we think those are the 5 parameters that completely describe this physical system that we're guessing, we could add more. We could have 10 parameters. It would just make our job a bit more cumbersome, and we'd find out that some of those 3 extra parameters wouldn't make any difference. But we could add surface tension, for instance, You wouldn't think that would have a case in this single phase flow problem. We could add, I'm not sure what else we could add, compressibility, for instance, but it would just complicate matters. So, K variables. So in this case we have 5 variables. We have velocity, density, viscosity, some length dimension, which is the diameter or the radius, and a pressure gradient. So five variables. We have mass, length, and time are the 3 potential dimensions we have. And the question is, do we have all of those represented here? Well, by inspection. Velocity is meters per second. So for sure we have length over time represented. Density is mass over volume. So we have at least 3 of these. So I guess the other one could be temperature, but we won't worry about that here. So it means that if we have 5 parameters and 3 dimensions, then we're going to have 2-dimensionless groups which will define this behavior. So what are the solution steps? We list all the variables. We've just done that. So we have variables that define the geometry, the fluid properties, and the driving forces. So the driving force is pressure gradient, the fluid properties are viscosity and density, not interfacial tension. And of course, unit weight would just be gravity included. And we have a length dimension. So we have 1, 2, 3, 4, and we had the state as well. We have also velocity. Velocity would be our dependent variable, I guess, in this case. And so what we'd like to do is be able to express each of our variables in terms of its fundamental units. And then what we do is we select repeating variables. We remove them from the list of variables that can be combined to give a pi group. And the repeating variable is one that typically has all of mass, length, and time exhibited in it. And so we'd like to choose those as repeating variables. And then from that, we figure out what the pi terms are just by working through them and finding out what the dimensionality of those individual terms has to be. So words don't matter. Let's go through it as an example. It's much easier to understand as an example. So this is our problem. So we have exactly the same properties as before. A length dimension, density, viscosity, and the velocity of flow. We're going to choose one variable as the dependent variable, which is a function of these others. We've said that we have 5 of these that we want to be able to describe. So the first step is to be able to figure out exactly what the quantities are for these. And so diameter is clearly just length. Density is mass per unit volume. Viscosity is Pascal seconds. A Pascal is equal to force over length squared times seconds, which is the same as force is equal to mass times, kilograms. Let's do it in the right units. So it's equal to mass times acceleration times seconds over length squared. And so if you write that out in units, mass is kilograms, acceleration is meters per second squared, seconds is seconds, and length is length squared. I guess I should have done, this should be t squared, right, in this terminology. And so what are we left with? We're left with mass, we lose one of the seconds, and so we'll be left with mass over length over time, right? Mass over length over time. So I can never remember what these are, but there's a quick way to do it. If you know that Pascals is force over area, you know that force is equal to mass times acceleration, you can always get them. So likewise, we can get all of these. We want to choose as our dependent variable the one that has all of these represented. So it could be either viscosity or pressure, because these are the 2 that have mass, length, and time all represented. We're going to choose pressure drive. Pressure drive in our particular case is pressure per unit length. So note that dPL is this, not this. Doesn't matter, we've just grouped it. And we know as a result of this, because we have 5 of these terms and we have mass, length and time all represented, then 5 minus 3 is equal to 2. So we know that we're going to get 2 pi terms. So let's come back to this. And so we're going to now use this equation. We have the dependent variable which we're going to use. And what we're going to do is we're going to choose 3 of these terms to combine. And we're going to take the first 3, not for any particular reason. We're going to take this one, and this one. Why do we want to do that? Well, we want to choose the ones that are simplest, I guess, but we want to make sure that they include all of the variables that are included in this dependent variable. So this is this. So they're simple, but they include length, time, and mass, but we have some simple ones. So here, this is what we're going to do. So now we're going to set this up to get the pi term. The pi term is going to include the product of the dependent variable and these 3 other terms. And we want the pi term to be dimensionless. And so this has to have no dimensions. So what we're going to do is we're going to take the dependent variable to the power 1. So it's going to keep its original terms. And we're going to multiply it by the other 3 terms that we've chosen, the first of our 3 terms. And we're going to figure out what the exponents we have to apply to these so that indeed this ends up being a dimensionless variable. That's basically it. So the power is, you've noticed the Euler number and the Reynolds number that we use to characterize behaviors are non-dimensional parameters. So the key seems to be, even though we're calling this subset of our class dimensional analysis, it's actually dimensionless variables we're looking for. And so what we can do is we can work out what the units are of pressure divided by length, and it's mass, length to the minus 1, time to the minus 2, divided by length. So that's where the second length term comes from. And we're going to define the parameters that define diameter, which is length to the power a, velocity, length over time to the power b, and density, mass over length cubed to the power c. And together, these have to equal mass to the power 0, length to the power 0, and time to the power 0, right? By definition. If it's dimensionless, this is our definition of having no dimensions in this. And so what we're going to do is we're going to look at, if you look on this side, first of all, take the terms that involve mass. Pressure has mass in it. Mass, bless you, to the power 1 is this term here. Diameter has mass in it not. Velocity doesn't have mass in it, but density does. Density, mass to the power c, is this term here. And it has to equal this, which is this. Okay? So that gives us one equation. If we want to be able to solve this to make sure that these a, b's, and c's are the correct powers, we need 3 equations to be able to solve this simultaneously. And so we go through to the next one. We look at length. Pressure gradient has length to the minus 2. Diameter is length to the power a. Velocity is length to the power b. And density is length to the power 1 over length cubed, minus 3c. And likewise for time, time occurs in here, minus 2. Time occurs in here, minus b. No time here. And so now we can solve the system of equations. So we know that c, for instance, is equal to minus 1, just by solving this. If we know what c is, I guess we know that b is equal to minus 2. And if we substitute in for b here being equal to minus 2 and c being equal to minus 1, then we know exactly what c is. Sorry. Okay. C being equal to -1, then we know exactly what A is. And so we have each of these. And so now we can just come back to this, and now we know that A is equal to the power 1, B is equal to the power -2, and C is equal to the power -1. And so the first pi term comes out of this, delta P over L, D to the power 1, V to the -2 is 1 over V squared, rho to the -1 is 1 over rho. And so we have a first term. And so what is this in terms of our first term? We could also write this out, I suppose, as being something that looked like this. So this term should look familiar. It's the Euler number, and multiplied by d over maybe L, right? Remember, if we scoot back to what we've done before at this, well, actually this, right? So we had an Euler number, and we had d over L was on the other side, but we could multiply both sides by L over d, in which case we'd have this, and this would be exactly what we have on the other sheet. And so we've known nothing about the mathematics of the Navier-Stokes equations. We've done it purely as a result of just substituting some variables and trying to figure out exactly what the magnitudes would be. Okay? So it's a recipe, if you like. So we said we had 2 pi groups. So we've got one of them, pi 1 is equal to the Euler number and some other stuff. Second group, we're going to take this dependent variable again, and we're going to use another pairing that would include now 2 of the other terms we had before, but now we want to use the extra term that we hadn't used yet, which is velocity. So let's go back down to this. Okay, I guess yeah, we've dropped the pressure, so yeah, that's interesting. Yeah, okay. So now we're doing it with the remaining variable, which is, did we use? Oh, we had V before. What did we use before? D, V, and rho. Yeah, okay. The others, so it's not that. Well, I lied. So we used V before. So yeah, we used D, rho, and V before. And so now we're going to want to use this in terms of the numbers. And so now we're going to run through there with the remaining numbers, the other groups. So we're going to add the other parameter which we used before. So the other parameter is delta P that we used as a dependent variable. Now we're going to use viscosity. We're still going to have diameter, velocity, and density included. And again, this variable has all of the units in it. So this will be to the power 1. These will be the power A, B, and C. So actually, this term really hasn't changed from before, right? If you look at this. And so much of this recipe is going to be the same. So diameter, velocity, and density is still diameter, velocity, and density. And so all that's changing is this front variable. And so viscosity, if we go for mass, viscosity is to the power 1. And this is the same as before. If we look at length, then this is to the power -1, which is this term here. And these 3 terms are exactly the same as before. And then for time, time is to the -1. And these other terms are exactly the same as before. It hasn't changed so much in this particular case, in that now we can get our value of C from this equation. We can get our value of B from this equation, which are these 2 here. And if we know each of the values of those, then we know that if C is equal to -1, and if we know that B is equal to -1, then it allows us to get our final remaining term. And so with that, we can just substitute in here. So D is to the power -1, B is to the power -1, and C is to the power -1. That's interesting. And so in other words, if we write this term out, this is to the power 1. So you know exactly, you can guess what this is going to be. Which is just 1 over Reynolds number, where the characteristic length in the Reynolds number is the diameter of the pipe. And so the big picture, I guess, whoops, I didn't mean to do that. I'm not sure what to restore is. The big picture is that what we've come out of this by doing is that we've really just assumed that a certain number of variables define our problem. And if we're clever about manipulating these variables, we can figure out the number of dimensionless groups that they fall into, and hopefully those dimensionless groups tell us something about the physical behavior of the problem. Yes, Daniel?
So if you had, can you use any...
You could choose any of the variables to do this, yeah.
Matter?
Yeah, it looks
so
like...
if you had taken out the length and just use the delta PL, then rho...
You can use... Yeah.
The same thing?
You will get a different set of dimensionless variables, but they'll reduce to the same ones.
Okay.
Yeah. And so the key here is that it's best to choose as the repeating variables. You saw that we chose pressure and we chose viscosity as the two ones in the different pi groups. They also happen to be both the most complicated ones in terms of the properties. They include mass, length, and time. And so that seems to be a rule. For exam questions, typically we'll say what to use, because you do get a different grouping of variables, but you solve the problem the same way. So, but you don't have to make an informed decision on the variables. You'll get something that you can manipulate into something that's useful. And so really what we've done is we've really just defined what we think the physical processes are that affect our system. We have fluid flowing. The drag on the side is due to viscosity. Therefore, viscosity might be important. You could make the case that density might not be important because it's all being driven by pressure. But certainly changes in velocity along a pipe would be driven by energy in the system. And to accelerate a fluid, you have to act against its density to be able to change its momentum. So density comes in through that. And so if you can guess what the parameters would be that define your system, some definition of geometry, the diameter of the pipe, the length of the pipe is in there, some definition of the fluid properties, which are density and viscosity in this particular case, and some definition of the response of the system. So the response of the system would be the pressure you have to apply to be able to drive a flow and the velocity you'd get after you've driven it. And so those are the 5 parameters that describe this behavior. And so what comes out of this is that we end up with a final relationship which says something like this. These are the 2 pi groups that we got. The first pi group was this one, and then the second pi group was this one, and this is just a function of, right? So Euler number, modified Euler number, right? This is delta P over delta L d over v squared rho. So this is Euler number times diameter to length ratio equals some function of Reynolds number. And so actually I think it's an amazing process in some respects. So we don't need to know we don't need to solve the equations for Navier-Stokes equations for flow, which anyway are only available for very simple geometries, like a tube and for a parallel-sided duct. and are only available for very simple flow regimes, laminar flow as opposed to turbulent flow. We don't have to solve those. And from this, now we can decide how to run our experiments to be able to do this, because this basically says that we should get a relationship that links Reynolds number with Euler number. And so if we take one pipe, it's a bit more complicated in this case. If we take a pipe, we would find out that if we run some experiments, what would it be? It's a bit complicated because we've got a velocity term here and a velocity term on this side, which makes it intellectually a bit tough. So I'm trying to think what this is. It will look something like this. We'll find out that this is take this on trust. We'll find out that we plot a friction factor, which will not to be confused as a function. So we will find out that we'll get a bunch of graphs when we talk about pipe flow that look like this. They're called Moody charts. And what they say is that the resistance to flow, the friction factor, which is either proportional to the Euler number or 1 over the Euler number, can't figure that out right here, that in the laminar regime there's a given relationship, and for pipe flow it's equal to 1 over 64 times Reynolds number. The 1 over 64 comes from the 32 that we saw in this equation before, so it comes from that. And as we go at faster and faster velocities, all of a sudden the flow, instead of being this laminar flow, breaks down into this turbulent flow for different diameters of pipe. And so this relationship is something that we can surmise by doing some experiments with different diameter pipes or different fluids, but nonetheless, in the laminar regime, there's a single relationship that we get for every single pipe, every single fluid, with every single density and viscosity. We get a single relationship, but when we deal with non-laminar flow, then it breaks down and we have multiple relationships. But nonetheless, we're guided by the fact that it's Reynolds number, which indexes the flow regime, and Euler number, which says something about either the force that's applied on a structure on the outside, or the force that's applied on the inside of a structure, on the inside of a pipe. And of course, we don't really care about what's inside the pipe. We don't really think of it as being the force you have to apply to be able to keep that pipe static because it's being flowed along. We think of it more in terms of the pressure drop you get in the pipe that you have to overcome with a pump to be able to do it. But they're the same problem. You could think about a pipe as being how much force you have to hold it in place to act against the pressure that's applied in the pipe, as opposed to the fluid pressure you have to apply to be able to drive the flow at that particular speed on the pipe. It's just the perspective of it.